Your test papers have been checked, so I will share those papers at the end of the class. I will ask someone from the operations team to WhatsApp you the checked papers. Huh? All papers have been checked. So in the last Monday, I didn't take class. On the last Monday, we started magnetic effect of current. In magnetic effect of current, we have discussed majorly this Bioximer law. So Bioximer law says if you have a conductor and some current is passing through that conductor, then that current will generate magnetic field. If you take a very small element of that conductor, means the element of some small length dl, the magnetic field due to the small length at point P is given by this expression, or it should be given by this expression. It's mu naught by 4 pi ideal cross r divided by r. It's given by this expression. This dl is the small current element. R is the position vector of the point at which you are calculating magnetic field with respect to this small dl element. We consider this dl element as the origin. When you take the cross product, then it comes out to be, if when you open this cross product, you will get this relation k idl sine theta by r square, where k is mu naught by 4 pi. Through this expression, you can decide the direction of magnetic field. See, no need to remember all these expressions. These were some conceptual questions that we have discussed. This is conceptual question. This is conceptual question. This is a conceptual question. The direction is important. The direction of magnetic field is important. Let's do the direction of magnetic. Did we discuss direction of magnetic field in last week? Ishika, Arpit, Rishma, Minashi. Did we discuss the direction of magnetic field last week? Am I audible?
Yes, sir.
So I'm asking, did we discuss the direction of the magnetic field last week? Okay. We did Bioximer law, this much you remember?
Yes, sir. This video.
This video. Okay, now let's. And we have discussed this thing also, like this is the expression in free space. If you take another medium, then instead of mu naught, you will be using mu r. Mu r is the relative permeability of free space. If you have a paramagnetic material, then this mu r is greater than 1. For ferromagnetic, very, very greater than 1. If you have a paramagnetic material, then mu r is just greater than 1. If you have a diamagnetic material, then your mu r will be less than 1. Now let's discuss the direction of magnetic.
Sir, can you explain the direction part again?
Yes, I am discussing it again.
Yes.
Now let's discuss the direction of magnetic field. See, in magnetics, the major issue is always the direction. The calculation of magnetic field is not tough. The major issue is with the direction. So let's see what is the direction of magnetic. Start with the direction of magnet. For the direction, for calculating the direction of magnetic field, we use this expression. What was Bioximer's law in vector form, Hishma? Hishma, what is Bioximer's law in vector form?
mu 0 by 4 pi I into dl.
Cross R, right? Divided by R cube. This was Bioximer's law in vector form. And this is your small current element, dl. And this is point P. You're supposed to calculate magnetic field at point. So the first thing is that magnetic field that you are getting from this expression, this dB, is coming from the dot product of dl as well as R. So your magnetic field should be perpendicular to both dl as well as R. So that's the first thing. The first thing is magnetic field. Magnetic field is perpendicular to both small current element dl as well as this position vector R. So magnetic field is perpendicular to both the vectors, perpendicular to dl as well as it's perpendicular to R. So direction which is perpendicular to both dl and R will be perpendicular to the plane containing dl and R. Okay, just do one thing. Draw this in your notebook. We will do all directions using the plane of your notebook. Draw this thing in your notebook, everyone. Draw this thing in your notebook. Then we will decide the direction.
Yes, sir. Done.
Done. Okay. So see, your magnetic field is perpendicular to this line element dl as well as this position vector R. So the direction which is perpendicular to both dl and R, there are two options. One is it can be either outwards, means if this is your notebook, if you draw this dl and R in your notebook, then this magnetic field B will be either out of the plane of your notebook or it could be into the plane of your notebook. It's either outwards or it's either inwards. These are the two possibilities for the direction of magnet. Now, whether it would be outwards or it would be inwards, to decide outwards or inwards, we have several rules. So here we will use right hand thumb. So in right hand thumb rule, what we will do is we will take our thumb and we will place our thumb in the direction of current. Like if I consider this is the current carrying conductor, if this is the current carrying conductor, then I will hold that conductor in my hand in a way so that the thumb points in the direction of current and the curvature of finger will give the direction of magnetic field. I'm repeating it again. Say current is going in the upwards direction. So hold this conductor in your right hand in a way such that thumb points in the direction of current in the upwards direction and the curvature of finger will give the direction of magnetic field. So this is the curvature. This is the
Magnetic
curvature.
field is anti-clockwise, right?
Magnetic field is, yes, anti-clockwise, but for different
Right.
points. Yes,
Tell the direction of fingers what will it give?
the direction of curvature of finger will give the direction of magnetic field. So I take my thumb, I place this thumb in the upwards direction, in the direction of current. This curvature of finger will give the direction of magnetic field. So magnetic field is going anti-clockwise. If I ask you to calculate magnetic field here, then the magnetic field lines will come outwards from this point. Here, the magnetic field lines will go inwards. Magnetic field is rotating in this way. At this point, it will come outwards. At this point, it will go inwards. So this is the direction of magnetic field always. So again, if I go back to the figure, I want to calculate the direction of magnetic field over this point. So what I did is I hold my thumb conductor in a way so that thumb points in the direction of current. Current is upwards. This is the direction of current. So my thumb is upwards. Take the curvature. Curvature is going outwards. From this point, at this point, the fingers are coming outwards. So the magnetic field is outwards at this point. And if I want to calculate the magnetic field here, then see, magnetic field lines are going in anti-clockwise direction. Over this point, they are coming outwards, but for this point, they are going inwards. So the direction is inwards.
Sir, I'm not getting this.
See, the magnetic field lines are getting anti-clockwise. Magnetic field lines are rotating anti-clockwise. So anti-clockwise means they are going in this way. Huh? So if I want to calculate the direction of magnetic field at this point, over this point, magnetic field lines are coming outwards. If you want direction of magnetic field at this point, then at this point, magnetic field lines are going inwards. So they are outwards, inwards, outwards, inwards. This is the direction of magnetic field. Is it clear?
Yes, sir. Yes, sir.
See, in magnetics, if you can't decide the directions correctly, that means you can't solve the numerical. Directions are very, very, very important. Minashi, Hishma, Arpit, Alia, is it clear the direction of magnetic field?
Yes, sir.
Yes, sir.
So how we'll decide the direction? We will hold the conductor in our right hand in a way so that thumb points in the direction of current. And this curvature of finger will give the direction of magnetic field. So curvature is anti-clockwise. So magnetic field is this anti-clockwise. Over this point, if you take this anti-clockwise curvature, over this point, it's coming outwards. Over this point, it's going inwards. So this is how we decide the direction of magnetic field. So it's outwards at one point and inwards at another. Okay, just tell me, if I say that current is going in the downwards direction, it's going downwards, huh? Hishma, what will be the sense of magnetic field? It would be clockwise or anti-clockwise?
Clockwise.
Sorry, Hishma?
Clockwise.
Clockwise, right, Arpit? It would be clockwise.
Yes, sir.
If I ask the direction of magnetic field at this point, what will be the direction? Inwards or outwards? Akshay?
Outwards.
Sir, outwards.
It's clockwise, na? So over this point, it's coming outwards. When it's coming outwards, this is the direction. Out. It's going outwards. And this point, magnetic field lines are going inwards. So this is it. So this is how we decide the direction of magnetic field using the right hand thumb rule. There are several ways of using right hand thumb rule, but the easiest is this. So direction is hold current carrying conductor in right hand in such a way that thumb points in direction of current and curvature of finger will give direction of magnetic. Curvature of finger will give direction of magnetic field. This is how we decide the direction of current using right hand thumb. There's one more, let's take one more example. What if current is going in this direction? Minashi, what will be the sense of current now? Sense of magnetic field?
Anti-clockwise.
Anti-clockwise. Okay, if I ask the direction of magnetic field here, what will be the direction of magnetic field? Sorry, at this point, A, inwards, outwards, what will be the direction of magnetic field, Minashi?
Outwards.
Outwards, okay. What about the rest? Okay, everyone, just write the directions in chat room. Just write the directions in chat room. Outwards, inwards. You will be having just two options, either outwards or inwards. And send it to co-host. I'm asking. Yeah, this is the current carrying conductor. I'm asking about the direction of magnetic field here. Akshar is correct. Noha is correct. Yashika is right. It's very, very easy. Just hold this conductor in a way so that your thumb is in the direction of current. Good, Ishma. Miraj. Arpit is right. Alia. Nabil Khan. Nabil Ahmed. Yes, Alia, it's correct. No, Nabil, it's wrong. Nabil Khan, Nabil Ahmed, it's not inwards, it's outwards. See, how we decide the direction? The current is going to the right hand side. So take your right hand, place your thumb to the x-axis in the direction of current. Now, this is the curvature of your finger. So over this point, which is above the wire, the curvature of finger is outwards, right? Bahar, outwards. Then if you take a point here below the wire, then the curvature will be inwards. It's going in this way. So if I take this wire, this is the sense of the current. The magnetic field. The magnetic field is going in this way. So for a point above the conductor, it's going outwards. Below the conductor, it's going inwards. So Nabil Khan and Nabil Ahmed, is it clear now that at point A, the direction will not be inwards, it will be outwards? Yes, Nabil. Here it will
Fingers
be outwards.
are inward, right? Fingers are inward, right?
Above the wire, the fingers are outwards. No? See, this is it. The finger is. You are taking right hand or left hand? You're taking right hand, na? So take your right hand, thumb in the direction of current. Just see the curvature of the finger. It's coming bahar. it's coming out of the plane of your copy. If you draw this line on your notebook and you place your hand in this way, then for a point which is above the wire, the fingers are coming outwards. Then they will go inwards if you consider a point below the wire.
Understood, sir. Understood.
Yes, Nabil. Nabil, your voice is cracking. So this is the thumb. I'm placing my thumb along the direction of current. The curvature of finger will give the direction of magnetic field. So for a point above the wire, the fingers are coming outwards. They're going in this way. Na? For a point above the wire, it's going outwards. And for a point below the wire, the fingers are going inwards. Nabil Khan, is it clear now? Anshika? Nabil, is this outwards, inwards clear now?
Yes, sir.
Yes, sir.
Okay. So this is how we decide the direction of magnetic field using Bioximer's law. Just note it down, then we'll start the numericals.
Sir, can you show what was there before this, sir?
Nothing. We started from here only.
Okay, sir.
See, direction is a major part of chapter number 4 and chapter number 5.
सर यहीं से स्टार्ट हुआ है ना आज से? See, if you can remember these 4 examples, 1, 2, 3, and if current is going to the left hand side, then here magnetic field will be inwards. Here your magnetic field will be outwards. In most of the questions, you will get these type of examples. Okay, okay, Alia. Can you scroll?
It's okay. Yes, everyone written?
Yes, sir.
Okay. The next are few small things about Bioximer's law, that you can use Bioximer's law for a small current element only. For using Bioximer's law, your DL element should be very small. The first thing. It's like just like Coulomb's law. Like you can use Coulomb's law only for a point charge. Just like Coulomb's law, you can use Bioximer's law for a small current element. You can't use Bioximer's law for a whole wire. So if you want to calculate magnetic field, you do a complete wire, then you have to integrate it within the proper limit. Next, it's your homework to write few similarities and differences in Bioximer's law and Coulomb's law. Similarities, I can tell you, both goes as 1 by r square. Both are valid for small current elements. The same way, find some differences between Bioximer's law and that's Coulomb's law. The Coulomb's law that we did in electrostat. Next, we need dimensional formula for magnetic field. Just remember, although dimensional formula is not a part of class 12 syllabus, but is an important quantity, you should know its dimensional formula. It will help you in your J exams. So for dimensional formula, use this expression. There is one expression which is F is Q velocity into magnetic field. From this expression, you can write that your magnetic field is force divided by QV. The force is M1. L1 T minus 2. Charge is 80, A1 T1. Velocity is L1 T minus 1. So the dimensional formula is it's M1 L1 and L1 will cancel out, it's L0. T1, T minus 2, 1 minus 1 will cancel out. So this is T minus 2. And this is A minus 1. This is the dimensional formula for magnet. Direction of magnetic field have already discussed. Note it down. Then we'll start some numericals of Bioximer's law. You can find these similarities and differences in CRT also. Written, can I scroll it over?
Yes.
Sure. Now let's solve this numerical. See, this is a small element, this red one, small current carrying element. The length of the element is 0.01. This is the current which is flowing through the element. The element is up to here only. You're supposed to calculate magnetic field over this point P. This separation is, let's say, 10 due to wire, small wire. The first question is, can I use Bioximer's law here, Minashi? Can I use Bioximer's law to calculate magnetic field of this small element?
Yes.
Yes. So what is the limitation for using Bioximer's law?
It is only valid for small current element.
Small current element. So it's a small current element. We can use Bioximer's law. So I write Bioximer's law in this way. It's B is mu naught by 4 pi I delta L cross R divided by R. See, I didn't write DL. I write delta L. I didn't write DL because DL is something which is differential element, very, very small. So I wrote delta L. DL means length is 0.000001 centimeter. DL is small differential element, but here it's not DL, it's delta L. So I wrote it in terms of delta O. Now let's write each and every value. Say current is given, current is 10 ampere. How much is delta L, Meraj? Meraj Rahman, how much is delta L?
So 10.
10 is delta L. So तुम. Delta L is the length of the current element, Meraj. What is the length?
0.01.
0.01. And what about the direction? Alia, what is the direction of this current element? I'm not asking about the direction of magnetic field. I'm asking about the direction of this length element. Nabil Khan, what's the direction of the length element?
So length of the electric field is outward, right?
No, not yet. I'm not asking about magnetic field. I'm asking about the direction of this delta L only.
Towards right.
Towards right. The direction of delta L is same as that of current. The current is going to the x-axis, so delta L is also along x-axis.
Yeah.
So I'll be using a unit vector I cap here. How much is R here? Anshika. Anshika, how much is R here?
So 10.
10. Good. R is the separation of the point from the small element. And what is the direction of R? R is along y-axis, so the unit vector is j cap. So we have everything in this expression. Now let's substitute the values. Anshika, what is the value of mu naught? This mu naught, what is the value of mu naught? Remember, it's 4 pi into 10 raised to the power minus 7 over 4 pi into current I. Current I is 10 ampere into delta L. Delta L is 0.01. I cap cross R, which is 10 j cap, divided by R cube, means the cube of magnitude of R, which is just 10. So it's 10 j cap, 10 j cap meter. Now see, this 4 pi will cancel this 4 pi. This is 10. We can take all these number outside the cross product. 10 into 0.01 into 10 divided by 10 cube, and this is 10 raised to the power minus 7. And you are left with only I cap cross j cap. Akshay, how much is I cross j? Yes, how much is I cross j? We did this thing earlier. Huh? We have revised cross product plus starting off.
I into j sin theta or k.
K cap, I cross j is k. So instead of I cross j, you can write k. So your magnetic field will comes out to be, this is 10, 10 will balance this thing, 10 by 7. So this is 10 raised to the power minus 10, right? I cross J is K cap. Unit is Tesla. So this is the magnet. K cap means inwards, outwards, right, left. What's the direction of K cap? Inwards, outwards, right, left.
Outwards.
Outwards. So this is how you can decide the direction. Just take your thumb, place your thumb on the direction of this thing. Along the direction of current, this curvature of finger will give you the direction of magnetic field. The finger is going outward, so magnetic field is coming outward. Okay, now note it down. This. So you can calculate directions from two methods. You can calculate directions by using Bioximer's law in vector form, or you can also calculate your direction using right-hand thumb rule also. Always apply right-hand thumb rule. Take your thumb, place your thumb in the direction of current to the x-axis. Your curvature of finger is outwards when you do calculation over this point. Over this point, it's outwards, and over this point, it will be outwards. Note it down.
Sir, won't the final answer be 10 raised to minus 8?
Minus 8. This is 3 now. So this 2, 10, 10, 100 into 0.01 will be 1. There's 3, it goes to the numerator, it will be minus 10. Minus 10, na? Minus 10. This is 3m, na? So it will go in the numerator.
So this question is from NCERT.
Yes, this short example of NCERT. Anshika, is it clear? Every step?
Yes, sir.
Ishma?
Yes, sir.
Ishma, just tell me if you stuck at any point. Huh? Because if you have issues in the starting of the chapter, then as we move on, the issues will increase. Because every new topic will depend upon the previous topic. If you're not good at Bioximer's law, then the applications of Bioximer's law would be an issue for you. Mehraj, clear? Mehraj. फिर सो गया ये. Yes, written. Everyone, Nabil, Akshay.
Yes, sir.
Okay.
Yes, sir.
So that was about Bioximer's law. Always remember that Bioximer's law is valid only for a small current element. But if you want to calculate magnetic field due to a wire, due to a ring or any other shape, then what you will do is you will calculate magnetic field due to a small current element and you will integrate it over the entire space. Like if I want to calculate magnetic field due to this complete wire, So what I will do is I will take magnetic field due to the small element and then I will integrate it over the entire. This is how we use Bioximer's law. Now we have some applications of Bioximer's law. The first application is magnetic field due to a straight wire, magnetic field due to a circular wire, magnetic field due to a circular arc. These three applications are in your syllabus. This application is in your syllabus, but not through Bioximer's law. This is in your syllabus using Ampere's circuital law, but we will do it like in some numericals of electromagnetic induction. You will need this straight wire. You should know how to calculate straight wire. So since not as part of syllabus using Bioximer's law, so we will not consider the derivations right now. We will do the derivation of circular wire. We will do the derivation of circular arc, but we will not do the derivation of straight wire. We'll directly write down its formula and we'll consider the cases. So let's consider the magnetic field due to a straight wire. Derivation is not in syllabus. So let's take a long straight wire. It's a straight wire. You're supposed to calculate magnetic field over this pointer. You're supposed to calculate magnetic field here. So this is a straight wire. This straight wire is carrying some current I. The straight wire starts from point A and it ends at point B. This is the perpendicular distance between the wire and the point, let's say. This angle is phi 1. This angle is phi 2. You're supposed to calculate magnetic field here at point. So to calculate magnetic field here, what we use is we take a small element dl here to derive. We take a small element dl. We will first calculate magnetic field due to this dl element here, and then we will integrate it over the entire space. When we integrate it over the entire space, what we get is, we get the magnetic field at P is, it's mu naught by 4 pi. It's I by A. It's sine phi 1 plus it's sine phi 2. This is the magnetic field due to a long wire. It's mu naught by 4 pi I by A sine phi 1 plus sine phi 2. To decide the direction of magnetic field, and just one more thing, see this A is not R. The R we that took here, this R and A are not the same thing. R was the position vector. A is not the position vector, it is the perpendicular distance between wire and the point. So for direction, we will again use right hand thumb rules. We'll place your thumb in the direction of current. The curvature of finger will give the direction of magnetic field. Here, the curvature is going outwards. Here, the curvature is going inwards. So magnetic field is outwards here and magnetic field is inwards. Note it down. Noah, clear?
Yes, sir.
So the derivation is not in Swift.
Derivation is not in space. Through Bioximer's law. We will derive this expression, but not through Bioximer's law. We'll do it using Ampere circuit. Can I scroll it?
Mechanics problem.
Haji, can I scroll it now?
Yes, sir. Thank you.
Akshay, when your schools will reopen? September.
Yes, sir.
And yours, Hishma?
So 22nd.
Pretty soon. Okay, after this, we have some special cases. The first case is, what if your conductor is infinitely long? Infinitely long means the ends of the conductor are going towards infinity. The conductor extends from minus infinity to plus infinity. And you want to calculate magnetic field over this point. When the length of the conductor increases, then this angle phi1 and phi2 will also increase. When the length becomes infinity, this phi1 and phi2 becomes 90 degrees. Phi1, phi2 becomes 90 degrees. If length becomes infinity, then phi1 and phi2 will become 90 degrees. So what we can do is we can just substitute the values of phi1 and phi2 here. Instead of phi1 and phi2, we can substitute 90 degrees. So when you do that, the magnetic field will become, it's mu naught by 4 pi. It's I by A. It's sine 90 plus sine 90. So 90 is 1, so 2 it will be. So the magnetic field is, it's mu naught by 4 pi. It's 1 plus 1, it's 2. So it's 2I divided by A. So this is the magnetic. If you can cancel this 2 and 4 pi, then it will become mu naught I by 2 pi. So this B is, you can cancel this 2. Mu naught I divided by 2 pi. So this is the magnetic field expression of magnetic if you have a long straight wire. See, this long straight conductor is given in NCERT. This is a part of your syllabus. The finite conductor is not a part of your syllabus. But to come to long conductor, you should know how this finite conductor works. This is part of the syllabus. We will derive it using Ampere's orbital law. We will derive it using Ampere's orbital.
Sir, could you show the right hand screw rule one more time?
Here. Just take your thumb. Place your thumb in the direction of current, and this curvature will give the direction of magnetic field.
No, sir, like on the notes.
On which point? P.
No, sir, above this right hand screw rule, you had written right there. You just scroll up a little bit.
Yes. Place your thumb in the direction of current. Curvature of finger will give the direction of magnetic field. So the same thing that we discussed in Bioximer also. Well, you can call it as right hand thumb rule, right hand screw rule, the same thing. Why we call this as screw rule, Akshay, is that your question? Akshay, why we call it as screw rule, is that your question? See the
Sir, I don't understand.
sorry?
I don't answer the question.
Okay, you didn't ask. Who asked the question then? Nabil? Anyways, I'm answering the question. We call it as right-hand screw rule because most of the screws are right-handed, which means if you rotate your screw in the clockwise sense, then it will go in the upwards direction. If you take your right hand, and if this is the curvature in which you are rotating your screw, then your screw will go in the direction of thumb. If you rotate it in this way, then it will go upwards. If you rotate it in this way, then your screw will go downwards. So most of the screw that we use are right-handed. So this happens in screw also. If you take a screw, you rotate it in the clockwise sense, it will go upwards. So you can call it as right-hand thumb rule, or you can write screw rule as well. So this is for a long straight wire. If you have a long straight wire, then this is the direction of expression of magnetic field. Okay, if I want to plot magnetic field versus separate A graph, what will be the shape of the graph, Bhishma? If I want to plot B versus A graph, what will be the shape of the graph? Bhishma. See, B is inversely proportional to A. So what will be the shape? Only B is inversely proportional to A. What will be the shape of the graph?
Sir, hyperbola.
Hyperbola. This will be the shape of the graph. When you increase A, then B will decrease. Okay, Ishma?
Yes, sir.
This is the shape of the graph. After infinitely long conductor, if I take a semi-infinite conductor, and we say that point lies near the end of the conductor. Semi-infinite conductor means one point is at a finite distance. Another point is going to infinity. So the point which is going to infinity, it will subtend an angle of 90 degrees. And another point is subtending an angle of 0 degrees. See why I'm taking it as 0. The angle phi 2 is in between these two lines. One line is the line of perpendicular distance. Another line is this line which is connecting the end to this point. This is these two lines. The angle between these two lines is phi 2. Now what happened if these two lines coincides? If these two lines will coincide, then your phi 2 becomes 0. So if point lies near the end, that means these two lines are coinciding here. This is the line which is perpendicular distance. This is the same line which is connecting the end of the conductor to the point P. So here, these two lines are coinciding. So your phi2 is equal to 0. So when I substitute these values here, then your magnetic field will become, it's mu naught by 4 pi. It's I by A. It's sine 90 plus sine 0. Instead of phi 1, I'm substituting 90. Phi 2, I am substituting 0. So your magnetic field, the expression of magnetic field will become, it's mu naught I divided by 4 pi A. The next case is, what if point lies on the axis? Axis means this is your conductor. Your point can lie anywhere on the axis, not on the wire. Means if this is the wire, I'm not saying that point will lie on the wire. It will not lie on the wire, but on the line joining the two ends of the wire. Here. Anywhere this point P1 and P2 can lie. This point P can lie. So here phi 1 will be equal to phi 2 equal to 0. So your B will be equal to 0. There won't be magnetic field over these two points. Because phi 1, phi 2 is 0. When you substitute phi 1 and phi 2 0, sine 0 is 0, you will get B equal to 0. If point lies on the wire, then magnetic field cannot be calculated. Then magnetic field can not be calculated using Bioximer's law. You can't use Bioximer's law if point lies on the wire. You can use Bioximer's law if point lies at any other point. But if it lies on the wire, then you can't use Bioximer's law. You will be using Ampere's law. And remember, NCERT have discussed only this case. But you may need other cases also. So I have discussed all cases here. Note it down. Nabil Khan, any doubt?
No.
Just note it down. Then start the numericals. Can I scroll it?
Yes, sir.
So
Like,
here,
scroll up little bit.
the next case we are using two conditions. One is wire is semi-infinite. Another, the point lies near one of them.
Yes, sir.
Okay. Can I scroll it?
Sir, could you show up again, sir?
It's okay. So remember all these cases. If your wire is infinite wire, then it's mu naught I by 2 pi a. If it is semi-infinite and point lies one of the end, then it's mu naught I by 4 pi a. If point lies anywhere on the axis of the wire along the length of the wire, then magnetic field is 0. Can I scroll it further?
Yes, sir.
And this last case, if point lies anywhere on the axis of the wire, then you can't calculate magnetic field using Bioximer law. You will use Ampere-Silverslaw.
सर केस 3 में भी तो ऑन द वायर लाइक है.
No, it's not on the wire. It's on the axis. Means on that point will not lie between these two limits. Point will lie beyond it. Wire will end here only. Yeah? Okay, let's solve this question. Huh? Let's calculate magnetic field due to two long straight wires over this point P. This is the point. The point P lies just at the center of the wire here. Separation of point P from both the wires is D. From first wire it's D, from second wire it's also D. You're supposed to calculate magnetic field at point P. See, to calculate magnetic field at P, When we write long wire means infinitely long wire. So at point P, magnetic field is sum of the field due to first wire plus the field due to second wire. This is the magnetic field at P. It's the sum of field due to both the wires. Noha, what will be the expression of magnetic field at point P due to wire I1? Just the expression I'm asking. It's a long wire, Noha. Noha is not in class. Nabil, magnetic field at P due to this long wire. Nabil Khan. Nabil Khan, are you in class?
Yes, sir.
I'm asking about the magnetic field at P due to this long wire having current I1. What is the expression of magnetic field? It's a long wire, infinitely long wire. Right, Alia? No, not that sine one. It's a long wire, Alia. Yes, Nabil Khan, what is the expression for magnetic field for a long wire, infinitely long wire? See, we did it just now. This is it. This is the expression, na? V naught I by 2 pi. Nabil, how much is A here? If I want to calculate field at point B, this is the formula I'm writing. V naught I by 2 pi A. How much is A here? Small a.
Is 2D.
2D or D?
Is D.
A is the separation from wire to point. Na? It's D. So it will be mu naught I divided by its 2 pi D. What is the direction of magnetic field here, Nabil? Inwards, outwards. What will be the direction of magnetic field here? Apply right in thumb rule. Nabil Ahmed, what will be the direction of magnetic field at P?
Inwards.
Inwards. Inwards is the right answer. See, take your right hand, place your thumb in the direction of current. The curvature of finger will give the direction of magnetic field. The curvature is going in this sense. Na? So the curvature will go in this sense. So it will go inwards. The magnetic field is inwards. Minashi, inwards means which axis?
X.
Which one? X axis or Z axis? Z, na? Which Z? Positive Z, negative Z?
Positive.
Inwards is positive Z. No, outwards is positive Z and inwards is negative Z. So which axis, Minashi?
Negative Z.
And what unit vector we use along negative Z axis? Yes, Minashi. Which unit vector we use along negative Z axis? Minus of k, right? Plus. Hishma, what will be the expression of magnetic field due to this second wire?
Mu 0 into I2 by 2 pi D.
And what will be the direction of magnetic field? Magnitude is right. Just apply right hand thumb rule. Hold this wire in your right hand, thumb in the direction of magnetic field. Where will be the curvature of finger?
It will be outward.
Okay. Yashika, what will be the direction of magnetic field here at P due to the second conductor? Yashika.
Sir, outwards.
Outwards. Arpit?
Yes, sir.
Magnetic field due to the second conductor at P. Yes. Nabil, see, Nabil Khan, it will be outwards, not inwards. See, hold conductor in a way so that your thumb is in the direction of magnetic field. and just look at the curvature of finger. Where is it going? If this is the wire, hold it in this way. In this region, just look at the fingers. Where are the fingers going? It's coming out of the plane of your copy, or it's going into the plane of your copy? Nabir Khan. Nabir Khan, to do
Outside.
outside. The easiest way to do is place
Yeah.
your pen on your notebook. Then put your thumb in the direction of current. Then take the curvature of finger. It's coming out. Huh? But if I want the magnetic field here, it will come out from here. It will go inside, right?
Yes, sir.
So over this point, it's outwards. It says outwards. So outward means which unit vector, Nabil?
Negative.
No. Negative is inwards.
Positive. Positive.
Positive. Next, what we can do is we can like this mu naught 2 pi d k cap as common, and you are left with minus I1 plus I. This is the magnetic field at point. Mu naught by 2 pi d k cap minus I1 plus I. This is magnetic. Instead of 2 conductors, you can have more conductors also. You can have 3, 4 conductors. Then what you will do is you will calculate magnetic field due to individual conductors, and then you will add them up. Note it down, please. No, this is point P. You're supposed to calculate magnetic field at point P due to this system. This system have 2 conductors, one long conductor and another long conductor. So at P, the magnetic field will be the vector sum of magnetic field due to individual conductors. So for the first conductor, I use this expression mu naught I1 by 2 pi d. For direction, we use right hand thumb rule. For the first conductor, the direction of magnetic field at point P is inwards. For the second conductor, the direction is outwards. So this is the magnitude. Inward means minus k cap. For second conductor, this is the magnitude. Only the current is different. Separation is same. Direction is outward. It's k cap. Then I just take some mu naught I by 2 pi d k cap as common, and it's minus I1 plus I. Noah.
Yes.
So, so can I scroll it? Sure. Now let's take this example. You have these conductors. This is conductor number 1, and this is conductor number 2. You're supposed to calculate magnetic field over this point. Do it and write your answer in chat. So for the first conductor, current is going along. Let's take another. I'm changing the direction of current. I1 is there. This is your second conductor. The second conductor is going into the plane. It's going inwards. Like if you take your notebook, the second conductor is going into your notebook. Into the notebook means your conductor is along which axis, Unif?
Sir, minus Z.
Minus Z axis. Your conductor is placed along negative Z axis. And you are supposed to calculate magnetic field over this point. Let's say you wish to calculate magnetic field here. For both the conductors, the separation is 2. Again, cross means inwards. Your conductor is placed along negative Z axis. So the 2 conductors are placed in this way. One is along y-axis, and another is inwards. This is how the two conductors are placed. One is upwards and the other is inwards. This is how two conductors, and this is the point where you are supposed to calculate the magnet. Do it. See, when you write answer, don't write mu naught. Write your answer in chat room. Don't write 4 pi. Write rest of the terms. Answers. It's a simple calculation. Just have two conductors, two magnetic fields. Just solve it like previous question.
फिर इसमें दूसरा कंडक्टर कहाँ बनाएंगे?
Here, na? This one. Current is going inwards. This second conductor is going inwards, negative z axis.
Sir, I2 is along Z direction, sir.
Negative z direction. Yes. Hishma, I2 is inverse akshay, inverse negative z axis. Hishma, just check whether both the magnetic fields are along k cap. Just check, is both the magnetic fields along k cap? I don't think both the magnetic fields should be along k cap. Answers. Yes, Nabil Ahmed seems correct. Akshay, Nabil Khan, Munib, Yashika, Noha, answers. Hishma and Minachi just check the directions due to magnetic field of conductor 2. Place your thumb in inverse direction now. Your current is inverse. And check for the curvature of finger, where your finger is pointing. Okay, Akshashika. Yashika, currents are different. I1 and I2 are two different currents. So you can take current as common. No answers. Okay, let's do it together. So the magnetic field over this point will be, okay, Akshay, yes, it seems correct. B1 is, it's mu naught I1 by 2 pi d. Let's calculate the direction. See, direction is straightforward. Current is going upwards. So the curvature of finger will go inwards here. Inwards means minus of k cap is the direction. Yes, Yashika, it's correct now. Plus, your current is going inwards. If current is going inwards, you can take your thumb, you can point your thumb in the inwards direction. And the curvature of finger will point to the right hand side direction, right? Curvature of finger will go to the right. Hishma, Minashi, is it clear? Say current is not upwards, current is inwards. So everyone just take your thumb, place your thumb in the inwards direction, means into the plane of your notebook. Place your thumb in this way and just check the curvature of your finger, where your finger is going. For the point upwards, your fingers are, the curvature of the finger is in this way. Over this point, the finger is pointing to the right hand side. Hishma, is it clear why I'm taking it to the right hand side?
Yes, sir.
Right hand side means which axis? It's x axis, I guess. So it's mu naught I2 by 2 pi d. It's I cap. Some were taking it along j cap. So it's mu naught over 2 pi d. So this is I1 I cap, I1 k cap, and I2 I cap. So it's I1 k cap with a negative sign plus I2 I cap. Yes, is it clear? The magnetic field over this point. So to calculate the magnitude of the magnetic field at a particular point, direction is very, very important. Always use right hand thumb. Do it. Nabil Khan, clear?
Yes, sir.
Do it. Tell me once you have written, we'll start the numericals of current electricity and start revision of current. Tell me once you have written, we'll move on to the revision of current electricity.
Done, sir.
Done. Okay. So Bioximer's law, the first application of Bioximer's law, which is a long wire, it's over. Then we have other applications, semicircle, full circle. But if you can solve straight wire, then all other applications are quite easy. Just practice right hand thumb rule. And yes, one more thing. Can we have an extra class on Friday? I wasn't able to take the class on Monday. Can we shift it to compensate that Monday class on Friday at the same time? No issues, huh? Okay, we'll take it on Friday. Huh? On only this. Okay, so let's stop magnetics here. In the next class on Friday, we will continue with other applications, and let's start with the revision thing. Huh? Okay, now let's start with current electricity, revision of current electricity. So we were doing questions based on circuits. Huh? Let's continue with circuits. Let's start with this question. You need current I1 flowing through 1 ohm resistor in the following circuit. So this is the 1 ohm resistor. You need current passing through this 1 ohm resistor. This is the cell of 1 volt. Let's start with this circuit. Akshay, let's start with you. Can you tell me the voltage drop across this 2 ohm resistor directly? Akshay, just look at this circuit and can you tell me the voltage drop across the 1 ohm resistor? Akshay, I can't hear you. Voltage drop across the
negative 1. No, negative I1.
No, I'm just asking what a voltage drop. 2 ohm. The voltage across 2 ohm. It seems clear from the figure, the voltage across this 2 ohm resistor. It's not negative or something. Minashi?
So 1.
1, right. See, this 2 ohm is connected in parallel. Like it's connected directly to this cell. Huh? So the voltage drop across this 2 ohm should be 1 volt. Clear, Nabil? Nabil Khan? This 2 ohm is directly connected to this cell. So the voltage will be same as that of the cell. It's across this 2 ohm, it's 1 volt.
Okay.
Okay. And what will be the voltage across this whole combination? Noah? What will be the voltage drop across this whole combination?
So 1.
This will be again 1. Now you have to decide how much current is passing through this 1 ohm. So for this, we can calculate the equivalent resistance of the system. 1 ohm, and 2 ohm. So if you want, you can draw it separately. You can draw this system 1 ohm, and this 2 ohm as a separate. This is 1 volt. Okay. How much is the equivalent resistance? 1 ohm in parallel and this 2 ohm in series. How much is the equivalent? What is the equivalent of 1 and 1 in parallel? It's half. And then 2 ohm in series. So it's 2.5 ohm. How much is the current through the system? Nabil Ahmed, how much is the total current through the system?
I1 plus I2, sir.
You have a total current I'm asking.
2I1.
Not 2I1. See, its total voltage is 1 volt, total resistance is 2.5. Yashika, what will be the total current?
So 2.5 amperes.
By R.
V by R, na? So it will be 1 by 2.5 ampere. So some 1 by 2.5 ampere current comes from here. How much is 1 by 2.5? It's 10 by 2.5, 10 by 25, 100, 100, 0.4. Huh? Some 0.4 ampere current through basket. So it's 0.4. What will happen to current when it reach here? See, your current will have two paths. So it will divide into two parts. 0.4 will divide into two parts, 0.2 and 0.2. So the current passing through this 1 ohm is 0.2 only. Clear?
Sir, for R equivalent, why haven't we taken the 2 ohm in parallel?
This 2 ohm and this total circuit, this upper wala, they are independent circuits. No? See, this and whole this are connected in parallel. So I'm taking the current which is passing through this system only. If I take this resistor also, then I'll be taking this total current, then this total current will divide into two parts and it again divides into two parts. I don't need current through this 2 ohm resistor, so I leave this part of circuit over here only. See, this and this whole part are in parallel, right, Yashika?
Yes, sir.
So if they are in parallel, that means they will have same voltage drop. He's not asking anything about this 2 ohm resistor. So I'm not taking this 2 ohm resistor. I'm taking this whole thing connected by the cell of 1 volt. Both will have voltage drop of 1 volt. Huh? If I have two resistors and I connected with this cell of 1 volt, voltage across this is 1 volt, voltage across this is 1 volt. If I have to solve this resistor only, then I won't consider it. If you want, you can calculate, you can consider this 2 ohm. The calculation would be lengthy, but in objective, you should know how to save time. Yashika, clear now?
Yes, sir.
Okay, just note it down. The question as well as the solution, we'll do the next one. Then we'll do question number 3. Do it fast. See, there is only one type of circuit that was not in NCRT, that was RC circuit having resistor and capacitor both. Otherwise, all other type of circuits you have already done. Just note down this third question. Yes, written. Nabil, Yashika, Akshay, written this question number 3.
1 minute, sir.
And when you write question, just highlight the given part. At least try to make a rough sketch while you are writing this question. You can't solve the numerical unless you understand the question. Make a rough sketch. Try to decide what you are supposed to calculate. We'll do it together, but at least try to understand the question. Make a rough sketch. Try to decide what quantity is asking you to calculate. Written? Minashi, Alia.
Yes, sir.
Okay, so you have a metal wire of 3 ohm resistance, elongated to make a uniform wire of double its previous length. So if you take a wire and you double its length, then its resistance will also get doubled. Resistance is directly proportional to length of the wire. Question 3 we will solve. Resistance is directly proportional to the length. Now, if he's asking you to double the length of the wire, that means resistance will get doubled. The resistance of the wire was 3 ohm. Now it will be 2 into 3. It will be equal to 6 ohm. This new wire is now bent and the ends joined to make a circle. So he make a circle out of the wire. If 2 points on the circle makes an angle of 60 degree at the center, so you can take 2 points. This is one point A. This is another point B. And this is the 60 degree. -60 of the wire. You need equivalent resistance between the 2 points will be. You need equivalent resistance between the points A. So you can consider this thing as 2 resistors. One is R1, another is R2. So you take this wire in the form of circle, you mark 2 points. For 1 point angle is 60 degree. Another angle will be 360 minus 60, 300 degree. So you have 2 resistors, one in the upper right corner, upper right portion, the lower portion. This R1 and R2 are connected in parallel. Now the only task is to get the value of R1 and R2. You know the resistance of the complete wire is 6 ohm. You need resistance of this portion. You know that resistance is directly proportional to length. So if we can calculate the resistance per unit length and this much length of the wire, we can calculate resistance R1 also. Let's consider the radius of the wire as some A. So resistance per unit length. I need resistance per unit length of the wire. I need resistance per unit length. Resistance per unit length is resistance R divided by 2 pi A. How much is R? R is 6 divided by 2 pi. This is resistance per unit length of the wire, 6 by 2 pi. Now R1 is the resistance for this much length. How much is this length? This length is subtending an angle of 60 degree. You can calculate this length using the formula of R. So resistance R1 is resistance per unit length, which is 6 by 2 pi A, multiplied by this length. See, angle is length of arc divided by radius of arc. So length is angle multiplied by the radius. Angle is 60 degree. Convert 60 degree into radius. 60 into pi by 180. Then multiply it with the radius. Radius is it. So this will get cancelled out. This will be 2. Pi a will cancel pi a. 2 will cancel 2. So R1 will be 1 ohm. 1 ohm, na? Yes, R1 will be 1 ohm. Total length is, total resistance is 6 ohm. If R1 is 1 ohm, then it's very clear that I2 will be 5 ohm. R1 and R2 are connected in parallel, then you can write that your R equivalent will be R1 R2 over R1 plus R2. How much is R1? It's 1. How much is R2? It's 5. 1 into 5 by 1 plus 5. So your R equivalent will become, it's 5 by 6 ohm. Clear? Five by 6, then in option 5 by 6. 5 by 3 is not any option. Sixty means angle is 60 into pi by 180 into a. Pi a will cancel this pi a. 60 will cancel this 3. 3 to the 6, 2 will cancel this 3. 1 ohm, 5 ohm. 3. Okay. R prime is 12 by a will be 4. Okay, yes. Sorry, when we double the length, then area of cross section will get half. See, area into length is equal to volume. Volume should remain constant. So when you double the length, then area will become half. And resistance depends both on length and area of cross section. So if this is wire, when you elongate this wire, then its length will increase, but area will decrease. So length will becomes double, then means area will become half. So if length becomes double, then area will becomes half. So this 2 will come to the numerator and it will be 4 times rho L by A. Means your resistance will becomes 4 times, sorry, not that 2 times. Is it clear why resistance is not 2 times, it's 4 times? Ishika, Noah, Arpit?
Yes.
Will be 4 times, sorry, not the 2 times. So the equivalent will be 12. So here it will be not 6, it will be 12. It will be 12. So it will not be 1, it will be 2. So 1 is 2 ohm, the total is 12 ohm. So if it is 2, how much is this one then? R2? Total is 12 ohm. If this portion is 2 ohm, then how much is this one? R2? Akshay?
10.
10. This will be 10. So you have 2 and 10 ka parallel. So it will be 2 into 10 divided by 2 plus 10. So it's always 20 by 12. So it's 5, 4, 5, 4, 3, 5 by 3. So this is your R equivalent, which is 5 by 3. Clear? So this will be your R equivalent, 5 by 3 ohm is your R. Note it down. So if your length becomes double, then area of cross section will get half and your resistance will become 4 times. Akshay, this one, I'm using the unitary method. The resistance of the complete wire is 12 ohm. I need resistance of this much of length.
Okay.
So what I did, I divided by the total circumference of the wire. This is resistance per unit length. Then for R1, I multiplied with the length of R1. Length of R1 is angle multiplied by the radius. L is theta.
Okay.
See, by the time we finish magnetics, we will complete the revision of current also. Yes, Nabil, just 1 second. Tell me once you have written this solution, we will come back to the question again. Yes, written.
Yes, sir.
This is a question, Nabil. We'll solve this question number 4. So after this question, just write this question, we'll solve it. Again, when you write question, try to understand what question is saying. Try to make a strategy. I believe it's an easy question. This is R5. Huh? No need na. No Wheatstone. For Wheatstone, your cell should not be over this position. Na? Cell should be in between these 2 points. Shall we start question number 4? Minashi, Akshay, Nabil. Yashika. Have you written this question number 4, everyone? Tell me once you have written question number 4. We'll solve this, then I will leave the class. Okay, let's. Akshay, written this question?
Yes, sir.
Now let's start with this thing. Yashika, is there any series and parallel combination here?
Sir, R3, R4, R5 are in series.
They all are in series. Now, if they are in series, how much is R3? R3 is 2, R4 is 5, and R5 is 25. These three are in series. So 20 plus 5 plus 25. This whole combination will be 50 ohm. This 50 and R2 are in parallel. How much is R2? R2 is 10. So the parallel combination of 10 and 50. So it will be 10 into 50 by 10 plus 50. So that is 500 by 60 gets cancelled out 50 by 6. Minashi, what about R1, R6 and this whole combination? What type of connection is this?
In series.
Series. So R1 is 15. Whole combination is 50 by 6. This R2 and 50 is parallel combination. Then you have this R6. How much is R6? It's 30. So we can take 6 as the LCM. So this will be 90 plus 50 plus 180. So this will be 140 and 180. 320 by 6. 160 by 3 is R equal. You have a cell of 15 volts. You can calculate the total current through the cell. Na? So it's V by R equivalent. So it's 15 by 160 into 3. So 53, 53, 52, it's 9 by 32. C option. Do it. Easy question. Say it's not a Wheatstone bridge. For Wheatstone bridge, your cell should be connected in these 2 points. Okay, good, Alia. Is it clear, Nabil, Minashi?
Yes, sir.
See, these all are our previous year's questions of JEE. So if you know your NCRT very well, then you can attempt, like for NEET, you can attempt 100%. For JEE, you can easily attempt 60-70% questions. But yes, your numerical solving skill should be very good. Most of the questions that you get in your entrance exams are based on the topics which you did in NCRT. But just the level of numerical is good. In the next class, also we'll revise some questions on circuit theory only. The major part of current electricity is circuit only. We'll be doing different types of circuits. And for those who will not be attempting for JEE or NEET exams, it's even good for numerical solving skills. This will help you in boards exams also. You can take it as a revision class only. Na? You have finished current electricity and you're getting one more class for the revision of current electricity. Okay, so everyone have written up to here? Written?
We'll stop here. We'll continue this in the next class. Huh? Okay, bye. Let's stop here. We'll continue this in the next class.